All right, 1st of October, let's take a look at, we've got 3 coordinate systems in 3 space. Appropriate. First, of course, is our rectangular one. And that's our usual case. Locate a point in space by an x, distance along the x-axis, a y, a distance along parallel to the y-axis, and a z. Okay? Okay? That's the height above the xy plane. This point is x, y, z. And that's our rectangular coordinate system. Here, I'll even put it, rectangular. Then we have what's called a cylindrical coordinate system, which is the polar coordinate system extended to 3 space. In the polar coordinate system, we have an r, a theta, just like polar coordinates. So what's r? R is this distance. Yeah, well. And we have a theta. Okay. And we have a z. It's the same z that we have. I know it. It's good. From the rectangular. Well, let's pause here for a second. You're going to be asked to go from rectangular to cylindrical, cylindrical back to rectangular. But you know what? We already have it since the z's are the same. But let's just review that a second. We know that x is equal to r cosine theta. We know that y is equal to r sine theta. Okay? What's that? The angle theta is down here. This is the angle.
It's measured from the positive x-axis.
It's always measured from the positive x-axis. What do you want? What?
Okay, it's fine.
Oh, okay. 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 All right. What else do we know? We know that r is equal to, well, let's say r squared is equal to x squared plus y squared. Okay. We've got this right triangle right here. And we know that theta is equal to inverse tangent y over x. And like I said, the z's are the same, so no problem there. So this is nothing new. This is what we've already had. But now, the spherical coordinate system is totally new. In the spherical coordinate system, we have a phi, an angle, that this line segment from the point to the origin makes with the positive z-axis. That's phi. We have the same theta as before. This theta is the same. But we also have a rho, the distance from the point to the origin. So in spherical coordinates, we have a rho, a theta, and a phi in spherical.
How do you spell phi? Just P-H-I?
Yes, yes. Yep. Okay. All right, well, here's what we've got to do. We've got to go primarily from rectangular to spherical, spherical back to rectangular. Once you get to rectangular, you can go to cylindrical. So basically what we want to be able to do is change from rectangular to spherical and back again. All right? Let's take a look. If this is phi here, this angle, what about this angle right here? What angle? That would also be phi. That's right. Why is that? Because we have 2 parallel lines cut by a transversal. These angles, what are these angles called when you have 2 parallel lines cut by a transversal?
7th grade term.
What's that?
I know that term from 7th grade.
Well, usually you get it in 10th or so with geometry. What is it? No, no.
Interior angles.
Alternate interior angles. Alternate interior angles. That's right. Alternate interior. Okay, that's exactly what they are. All right, so let's look at this triangle right here. This is a right angle, by the way, right there. Okay? So, here's what we want to do. Let's get, I'll tell you what, let's do, Omar, you made it. Wow, good deal. Okay, what we're doing is we've got rectangular coordinate system, a cylindrical coordinate system, and a spherical coordinate system. And right now we're going to go from rectangular to spherical and spherical to rectangular. So let's do that. Let's find out, let's do it this way. Let's start with rho. What's that distance in terms of x, y's, and z's? So if you're given x, y, and z, you can find rho by, what's rho equal to?
R versus z squared, so R squared would be a squared plus z squared.
Yeah, and then take the square root of it. Wow, pretty good. Or, look at this, the distance formula from here to here. What's that distance from a point to the origin? It's the square root of x squared plus y squared plus z squared, which is just what he said. Okay? He did a little bit roundabout way, but he got it. You had it. That's pretty good. That's what rho is. Theta is the same thing as before. Inverse tangent y over x. That doesn't change. Okay. What about phi, though? That's a little weird here. Let's take a look at this. Let's take a look at this triangle right here. In that triangle, if you take a look at cosine phi, it's equal to, it's z, okay, adjacent over rho. That's exactly what it is. Okay, check it out. It's the adjacent side over the hypotenuse. What's rho? We just said what it is. Square root of x squared plus y squared plus z squared. Therefore, phi is equal to the inverse cosine of z over the square root of x squared plus y squared plus z squared. And it's not nice, but that's what it is. Okay? Okay? Now, we got to go the other way as well. We need x, y's, and z's in terms of rhos, thetas, and phis. So let's take a look at that. What do we know? We know x is equal to r cosine theta. Here's r. Let's take a look at that same triangle. Okay? And what I want to do is get r in terms of phis and rhos. Okay? Here's what we have. X is equal to r cosine. And I need something for r. Looking at this triangle, what trig function should I use? What's that? Sine. Okay, good. Sine of phi is equal to opposite r over rho, hypotenuse. That tells me that r is equal to rho sine phi. Therefore, x is equal to rho sine phi cosine theta. That's x in terms of rhos, thetas, and phis. Y is equal to, what's y equal to? R sine theta. So it's rho sine phi sine theta. I know, this is killer stuff. All right. And let's take a look at z. Z is a little bit different here. Okay? Let's take a look at z. But z is easier. In this same triangle here, I've got z as part of the triangle. That makes it a little bit easier. If you take a look at cosine phi, for example, that's equal to z over rho. Therefore, the z is equal to rho cosine phi. Okay? If you're given rho, theta, and phi, you can get x, y, and z. And I believe the WebAssign will do just that. Okay? They'll give you some of these. For example. All right, how are we doing so far?
Not as bad as I thought it would be, to be honest.
It's not that bad. And we don't... Here's the thing, though. You have to make the transition from one to the other. That we're going to have to do on occasion. But most of the time what's going to happen is when we use spherical coordinates, it's because we're dealing with a sphere. And we'll go right to spherical coordinates. We won't have to mess around with the rectangular. As a matter of fact, there's one problem that we're going to do, and we're going to set it up in rectangular. We're going to have a triple integral to do, and it's going to be horrendous in rectangular. It's going to be doable, but still difficult in cylindrical, and it's going to be really simple in spherical. And the reason for that is because the equation of a sphere in spherical coordinates, if you have a sphere, here, all right, is everybody else set with this? Okay. If we have a sphere, here, let's take a look at this. And then we'll do one of those problems, translate it. But let's just check this out. Let's suppose we have a unit sphere. Okay. Let's find the equation of this unit sphere in rectangular, cylindrical, and spherical coordinates. Okay. First of all, what is the equation for this sphere in rectangular coordinates?
Square plus y squared plus c squared.
Perfect. Thank you very much. Okay. That's exactly what it is. What's the equation of this sphere in cylindrical coordinates?
R squared plus z squared is 1.
R squared plus z squared is equal to 1. That's exactly right. You replace the x squared plus y squared with an r squared, you give it r's and z's. That's exactly what it is. What's the equation of this unit sphere in spherical coordinates?
We just found out x and y and z, so squared them out.
So what's your equation?
Square root of the rectangle. No.
It's rho equals 1. That's it. That's the equation. Okay. X squared plus y squared plus z squared is rho squared. That's equal to 1. Take the square root of both sides, you get rho equal plus or minus 1. Throw out the negative 1, because when rho is equal to 1, that takes care of the negative 1 by going all the way around. Okay. Rho equals 1 is the equation of the sphere.
Because rho is the distance, right?
Yes.
So it's just 1.
Just 1.
From the origin.
1 from the origin. Every point on the sphere is a distance 1 from the origin. That's what a sphere is. It's the very definition of a sphere. This is why when we deal with spheres and we have to find some volumes or some center of mass, a varying density of a sphere, we definitely want to be in spherical coordinates, because the equation of a sphere is so simple. It's just a constant. And that's what we're going to do. So there's that in all three. We're going to find each coordinate system is going to be used in a particular situation where it's easiest to do the problem. Okay? And we'll do that. That comes a little bit later on. Right now, however, you should be able to take something in space and translate it to each of the coordinate systems. So if you're given this point in rectangular, let's say you're given a point 3, 4, 5, 3, 4, 5. In rectangular, you should be able to find out, translate it into cylindrical and spherical. Okay? It does get a little messy, however, but that's the way it goes. And I think WebAssign asks for these things to like 17 decimal places, no, like 3 or 5 decimal places, which is not really necessary. Maybe it's only 3. Maybe I'm exaggerating here. Hopefully I'm exaggerating. Okay, so let's do it. Let's go to cylindrical coordinates first. In cylindrical coordinates, we need an R, a theta, and a z. Okay? So, what do we have? For this point 3, 4, 5, what would R be?
Square root of 25x.
Square root of 3 squared plus 4 squared?
What's that?
Square root of 3 squared plus 4 squared?
You bet. What's that?
5.
X and y.
5. That's it. Now, you're going a little bit overboard there, Gina. I think you were back here. You were doing this thing or something. Now you're going to the whole sphere. All right, it's 5. Okay, that's this distance here. Here's what we got. This is 3. This is 4. This is 5. Can you still read that? I'm writing real small. But boy, this screen is really nice, though. All right, that's okay. It's really nice. Yeah, R is equal to 5. What's theta equal to?
Inverse tangent of 5 over 4.
Inverse tangent of what?
4 over 3. Sorry.
Yes. Inverse tangent, 4 over 3. And z is the same z as from before. It's 5. So that's that. Let's do spherical coordinates. A little bit more difficult here. What we have to do is find a rho, a theta, and a phi. Well, what's rho? What's that?
2 squared of 5.
2. Oh, you already simplified it. Holy mackerel. Okay, so 3 squared plus 4 squared plus 5 squared squared of 50. Wait, what'd you say it was? 5 squared is 2. That's pretty good. All right, 3 squared plus 4 squared plus 5 squared. 9 plus 16, 25, and another 25 squared root of 50. 5 squared to 2. Good job, though. That was fine. Okay. What's theta equal to? We already know it. Inverse tangent, 4/3. And what's z now equal to? I mean, phi. Sorry. Yeah, it's the inverse cosine of a bunch of stuff. It's z. Okay. So it's z. It's 5 over the square root of 5 squared to 2. So it's the inverse cosine of 1 over the square root of 2. Wow, we know what this is. What is that?
5 by 6.
What is it?
5 by 6.
Pi over what?
6.
I'm not hearing you right.
5 by 6.
Pi over?
6.
No.
Pi over 4.
Pi over 4. I was trying to help you out, man. Trying to help you out.
You would think you couldn't actually hear it.
Yeah.
It's not that outlandish.
Most of the time that's true. I can't. Yeah. All right. But anyhow, it's pi over 4. But usually that would come out, you just leave it that way. All right, so let's see. We changed from rectangular to cylindrical, rectangular to spherical. We should do the other way around. Let's do one spherical to the other two. And actually, spherical to rectangular is all we really have to do. Let's do that. And we got a couple other little things to do, and then we're going to be done. Let's suppose we're given spherical. Now I'm going to still label these X, Y, and Z. And
But you can still label them X, Y, and Z.
yeah, the axes are still X, Y, and Z axes, though. Yeah, which is kind of weird, actually. But let's take a point. Let's say in spherical coordinates. Let's say we have let's say rho is equal to whatever, 1. Phi is equal to, let's say, pi over 6. And theta is equal to pi over 4. Okay? What we want to do is find x, y, and z. X would be equal to. Now, am I going to ask you to memorize these? No, I am not. As a matter of fact, when we need them for the triple integral, there's an integrating factor, rho squared sine phi, that we're going to need. But I'm going to give you that form as well. All right, so basically what you're going to have to be able to do is take something like a sphere and know that what its equation is in spherical coordinates. When we get there, it'll be pretty clear. All right, x is equal to rho sine phi cosine theta. So x is equal to rho sine phi cosine theta. So we get 1 sine of pi over 6.
1/2.
Yeah, out of the way. He's back on again. All right. And cosine. And I'll rationalize that. Square root of 2 over 2. So you get square root of 2 over 4. Y is equal to 1. It's R. Rho sine phi again. But now sine of pi over 4. Whoa. And what do you get? The same thing, because sine and cosine are the same, so you get square root of 2 over 4. And the z is equal to rho cosine phi cosine pi over 6.
Square root of 3 over 2.
Yeah, you bet it is. That way. Okay. Okay. Just a couple other things here. One other thing is, we saw that rho equals a constant is a sphere of that radius. Okay, rho equals 6, for example, would be a sphere of radius 6 whose center is the origin. What do you get if you have phi equals a constant? Let's say phi equals pi over 6. What would that describe? What surface would you get for phi equals pi over 6? Well, what do you think?
Plane?
No.
Yes.
What?
Disc?
No.
A cone?
Cone is correct. Because what happens is all the points on the cone have an angle of pi over 6. Now, these over here would still have a pi over 6. It would be a cone. Okay. That's what you would get. So I think there's one example where we need to find the volume. Actually, we're going to be looking for the center of mass of an ice cream cone of varying density, where the density is proportional to the distance from the xy plane, kz. And we're going to use spherical coordinates, and we have to get the equation of that ice cream cone, which is a wedge out of the sphere. Okay, and we're going to do that in spherical coordinates, but that's later on. What's that? Yeah, that's true. I always solve that problem because it's gone instantly, practically. And then we all know where it goes to. Oh, boy. All right, but anyhow, that's the last section. You're going to have to do these conversions. It's basically what you're going to have to do in this last section. I don't think there's a heck of a lot more. There's some basic shapes, perhaps. But basic conversions. Any questions at all? Anybody? Yes?
Can we get a roadmap for the test like we did for the last
A
one?
roadmap? Yeah. Yes, you are. When's the test? Thursday? A week. We have tons of time. Oh, my goodness. We have too much time. Yeah, we will. I will let you know what's on that test. I'll give you section by section kind of a thing.
Take a couple more days off.
No, I got to tell you, it used to be very simple. You say to the dean, our other dean, our first dean, I'm taking a personal day off this day, and he writes back, okay. Now I wrote to her. We're in another division now because we got kicked out of the other one there, basically, and
I was making trouble, Burns.
And that's the reason too, because the math department is pretty proactive about what we do, though. We'd let people know we want to do this, we want to do this.
Calculated.
Yeah, well, I don't know about that, but anyhow, so I said, I'm going to take this personal day off, and she wrote back, said, well, let's see, what are your lesson plans? What classes do you have? What are you going to be? Who's going to be taking care of your class? And blah blah blah. So if anybody asks you what you're doing Friday, you tell them there's a special assignment in WebAssign that you're supposed to be doing. You didn't have to tell her that. I don't know if she's going to come around and inquire or what, but there you go. All right, so, all right.
You recorded it.
See ya.
No.